and to the people who have joined online. People at Ron Granger who read some of the work and others at the Newcomen Society, thank you so much for helping me towards this. But I'd like to start by dedicating this lecture to the memory of Ken Kiss, curator and director of the Crystal Palace Museum, who died just a few weeks ago. Without Ken, I would never have been able to carry out the work and the threads of the Crystal Palace, and I'd like to dedicate this lecture to Ken's memory and send my thoughts to his family as well. Thank you. Okay, so I've put the title up as Truth, Threads and Touch. I'm going to discuss the truth of surfaces. For example, here are two of Joseph Whitworth's surface plates alongside a liquid mercury mirror, which is the standard for flatness in Germany. I'm going to talk about the standardisation of screw threads, the work that me and Ken carried out together with the Crystal Palace Museum. And finally, I'll discuss the shift from sight to touch and measurement, something that Joseph Whitworth demonstrated at the Crystal Palace when he won a gold medal for his millionth measuring machine. So this talk examines the notion that humanity lies at the centre of technical objects and practices that might seem alienating to people who don't understand them. So using the three papers that Whitworth published on flatness, screw threads and measurement, my argument is that the standards that we have concerning flatness, measurement and threads originated in workshop practice rather than theory. So I'm going to discuss how Whitworth's practices have persisted into this day. Okay? So these are the three papers. You can see Whitworth delivered these papers in front of the British Association in Glasgow in 1840, the Institute of Civil Engineers in London in 1841, and the Institute of Mechanical Engineers in London in 1856. And Whitworth was not precious about his work, didn't patent any of the things here. Instead, these went into threepenny mechanics magazines and had a massive dissemination. So I'm not going to hide my admiration for the likes of Henry Maudslay or Joseph Whitworth, Richard Roberts, William Fairbairn and James Nasmyth. And each heap will feature here in my discussion of their considerable achievements. What these people do have in common, or did have in common, was that none of them darkened a university and that their workshop practices created the international engineering world that we have today. Now, many argue that during the 18th and 19th centuries, innovation indeed emerged from workshops. Frank Weinhold writes in Classical and Geometric Theory of Chemical and Phase Thermodynamics that before the steam engine, before Newcomen in 1712, no proper scientific foundation existed for understanding how a steam engine works. Of course, the second law of thermodynamics came out of observation of the engine. The engine didn't derive from theory. And as Weinhold writes, as aptly remarked by science historian L.J. Henderson in 1917, science owes more to the steam engine than the steam engine owes to science. Henderson's assertion goes against the notion that innovations came from the top down. Now, as I said, neither Whitworth, nor Matthew Bolton, nor Richard Roberts, or Henry Maudslay had a college degree. All of them completed craft apprenticeships, but all at the same time studied the scientific theories of their day. Now, there's some pushback against that. Civil engineer Samuel C. Floorman has written that real engineers are professional engineers with college degrees. The rest, according to Floorman, are technicians or mechanics. Floorman exhibits that top-down approach, defining engineering as the art or science of making practical application of the knowledge of pure sciences. Now, that way of looking at engineering has theory, direct and practice. And thinking about that period from Newcomen's atmospheric engine until the Great Exhibition, that seems to me back to front. Was it the high heads directing people or the people with dirty hands in the workshops that drove innovation of the period? It's an important question. As K.R. Gilbert, Keith Reginald Gilbert, former curator for the Science Museum, wrote, in 1775, the machine tools at the disposal of industry had scarcely advanced beyond those available in the Middle Ages. By 1850, the majority of modern machine tools had been invented. Now, Gilbert's writing in 1956, but a lot of that stands today. Control systems might have changed, but if you think about cutting tools, most of modern cutting tools were invented in that period. So who gets the credit for this? The theorist or the craft engineer? So let me frame this a little bit. Now this is the French philosopher Gilbert Simondon, who wrote his PhD in 1957 on the mode of existence of technical objects. And Simondon argues that the cultural world behaves towards the technical object as a man to a stranger, carried away by a primitive xenophobia. What Simondon argues is that there's an alienation that most people have against technical objects and machines because they don't understand them. But what he points out is that at the centre of every technology, of every machine, there's a human locked up within it. Humanity lies at the centre of technology. And that's what I'm going to talk about in here. Technologies might appear alienating, but the key thing to remember is that all technologies have humanity at their centre, and none more than the examples I'm going to give here on the true plane, threads, and touch. Okay. Let me begin with the true plane. I'm going to go in chronological order. I'll start with Whitworth's paper delivered in 1840. So pictured here are two surface plates that a kind curator at the Science Museum sent me pictures of just a few weeks ago. And they're currently held in Kensington. These were created by Joseph Whitworth. And you can see how heavily ribbed they are to make sure that they're rigid. Now, Whitworth's paper on plain metallic surfaces and the proper mode of preparing them was read at a meeting of the British Association in Glasgow in 1840. And it was published just a few months later in the Mechanics magazine in 1841 for a price of threepence. And as I said, that magazine had a long reach. And Whitworth, as a writer, is very efficient and very practical. Much of what he writes is about workshop practice, how you achieve the things that he achieves in his factory. Now, these plates are so flat that if you move them together, the pressure of the atmosphere will hold them. That's how accurate they are. If you lift one plate, it will hold the other. It will stick to it. Another way of demonstrating the remarkable flatness is to slowly descend one surface on top of the other. The upper plate will then float in a bed of air. Now, as Whitworth wrote, neither of these conditions could be met without extreme accuracy in both. So he brought these plates with him to the lecture. Now, why was this important? Well, Whitworth knew that everything that we make is based on a datum point, something flat to work from, something that we believe is true. Because if it's not true, everything we build from that point will replicate the inaccuracy that's already there. So as Whitworth said, the true plane is the foundation and source of all truth and mechanism. And I think we can extend that point. I think the notion of a datum point could be applied as much to a philosophical position or mathematicians needing a lemma to work from as it can in engineering. You have to stand in a position that you believe represents truth before you can create anything. Now, we know as engineers that perfection is impossible. Even that Mercury mirror that I showed you at the start isn't exactly flat. It's affected by the curvature of the Earth. But it's true enough to build up from. So what Whitworth did is he developed a system for creating these truthful flat plates. And the way he did it was using something he learned in Maudsley, Henry Maudsley's factory in Lambeth, where he went when he was 22. Because what Whitworth realised was that machines were not capable of the kind of accuracy that was needed. Okay. Now, Whitworth had begun his apprenticeship at the age of 14. And he gained as much experience as he could in Derbyshire, and then Manchester. He went to the best factories he could find to increase his knowledge, and he moved to Maudsley's Lambeth workshop when he was 22. And here he found a factory where they were beginning to standardise threads within the factory, and also interested in making true planes. Now, Whitworth exhibited these plates because of the high degree of truth that they possess. Because machines have limits. So what he did is he used 3 plates that would be planed with a machine and then filed by hand. So here's a planing machine, Richard Roberts, found it in the Science Museum from 1817. And you can see the single point cutting tool will plane a flat surface, but that's not good enough, and neither is grinding or filing. What you have to move towards is scraping. So what he would do is he would get 3 plates, he would coat one with oil and ochre. Later, in my time, Prussian blue would be used, and it would be rubbed with another plate. Now, the high spots would then be shown on the plate and scraped off with a worker with a hand tool. But there could be a concave and convex surface there, so you have to bring in a third plate to ensure that that's true. And working between 3 plates and hand scraping away high spots, Whitworth established something superior to machining for accuracy. Now, flat plane surfaces to act as references form the basis for measurement, and they're essential to machine tool manufacture and mechanical engineering. And I just want to show you, so you can see here Fairburn is saying when he first entered the city, the whole of machinery was executed by hand. Then with the likes of Maudsley, Richard Roberts, Whitworth, we have the improved lathes, planing machines, but even that's not quite good enough. We need to move back to handwork. And Whitworth found some pushback in this. Now this is a picture of the factory I served my time in. It's Weir Pumps in Glasgow. It's from round about the First World War this picture was taken. And you can see these workers using surface tables. And if anybody has ever scraped a surface table, you remember what a laborious job it is. And Whitworth's workers rebelled against it at first. If you look at his papers, there's a footnote there. And he says, when grinding was first discontinued in the workshop of Messrs. Whitworth and Co., no mechanic could be induced to take the work in the same terms as before, onto the supposed extra labour of scraping. So the workers thought this was a backward step compared to their new modern machines. Yeah. But Whitworth says, but experience has entirely removed this prejudice, and the work is now done with greater dispatch. So he managed to convince his workers that by bringing another step on beyond the machine, they could achieve much greater accuracy. And here you can see the same factory 100 years later. Again, someone marking off from a surface table. Not quite as tidy as the previous surface table we saw, but messier than that one. But nonetheless, the same job being carried out here, marking off on a surface table. Now, unbelievably, and I find this is something that might be difficult to credit, but if you've got a surface that's a large surface, this is still the best method. Even today, 21st century, 2026, is still the best method. So Graham T. Smith in Machine Tool Metrology says, a surface that's been prepared by scraping is generally considered to be superior in its overall accuracy and flatness to that produced by the manufacturing processes of either precision machining or from surface grinding operations. Okay? Although the lapping technique can be equal or often exceed that scraping, but this is normally over a small distance. So lapping again when you lap 2 surfaces together. It should also be emphasised yet again that both lapping and grinding operations do not achieve the long distance flatness characteristics of a quality scraping operation. So this process that Whitworth talked about in Glasgow in 1840, creating flat surfaces through a 3-plate system of scraping is kind of unbelievably still one of the best methods, or still the best method for achieving a flat surface over a distance. Okay, so again, humanity, human practice at the centre of engineering. I want to move on to the second. That's a paper that he wrote on standardisation of screw threads, delivered in London in 1841. Let me just get back and show you the paper. This one here, Uniform System of Screw Threads, delivered to the ICE in 1841. Okay, so this is the work that I was privileged to do alongside Ken Kiss, who was curator at the Crystal Palace Museum. Okay, so I want to move on to Whitworth's second paper on screw threads and a problem. How was the Crystal Palace, built in 1851, built in only 190 days, using, as Ken calculated, around 30,000 nuts and bolts, when there was no standardised thread form until 1905? How was it possible to build it that quickly when there was no thread form? And you can see here pictures of some of the, well, there's a column here, and these are taken from the drawings of the Crystal Palace. And what's interesting to note there is you'll notice that if this was a modern engineering drawing, you'd see the thread form specified. Instead, they've only specified that the bolt diameter is 7/8. They've not specified anything to do with the thread form, because there isn't one. There isn't an established one to specify. So I've poured through the engineering drawings for the Crystal Palace. You can find them in various places. You can find them in the Dana Library at the Science Museum. The Saffron Walden Gibson Library actually holds them in full as well. I've poured, that's near Cambridge, poured over them. There's no standard set there at all. So I'm going to talk about this. So in this part of the talk, I'm going to discuss how I tackled this. How did it happen? So through Ken, I managed to access original nuts and bolts from the Palace. And using the kind of technology available in the period, the screw cutting lathe, only available from about 1800, I remade the bolts, establishing that a vernacular workshop practice was in use by industry long before there was one sanctioned by the state. Okay. So the Great Exhibition of the Works of Industry of All Nations of 1851 was the showcase for the innovations of the previous half-century. The exhibition caught the public imagination, and then about a third of the population of Britain went to this. Around 6 million people visited the exhibition. And the palace designers, Joseph Paxton and Charles Fox, created a new building that was a departure from traditional materials and methods. So this structure, which used horizontal and vertical cross bracing to carry wind loads, was constructed in 190 days. So with a target area of 800,000 square feet and an upper cost limit of £100,000, as Bill Addis says, not only would this be the largest building ever constructed, it would also have to be cheaper per square foot than any building built previously. So it had to achieve these two things. Now, proposed only in 1849, the method of its procurement was remarkable. The design competition was launched the 13th of March, 1850. The deadline was less than 4 weeks later, and the building opened on the 1st of May, 1851. So there'd been 253 submissions to the competition, but none were deemed suitable by the Royal Commission's Building Committee. And instead, the committee put forward their own design, and it's unlikely that a brick-built building could have been built on time. So Paxton's drawings, produced by engineers at Fox Henderson's, were created in a period of 7 weeks and accepted on the 15th of July, 1850. Now, the palace was huge at 1,850 feet long, and it would grow on a summer's day around 12 inches, 30 centimetres. That's how big it was. Just the heat would grow it, and I'm going to talk about this sort of thing later on. In order to make it so quickly, they went for standardisation. So 2 lengths of standardised cast iron columns were used in the structure, and then the ground floor columns were 22 feet long, and those above were 20 feet. And girders were also standardised at 24, 48, and 72 feet long. So the 24 feet girders were cast iron, and the girders of 48 and 72 feet were wrought iron to cope with tension. As you'll probably know, cast iron is very good under compression, but quite weak under tension, and wrought iron is better. So they worked that out. So there were 3,300 columns in the building, and all were faced in lathes to give them consistent lengths and flat faces, so they wouldn't have to mess around with packing to get the heights right. And these columns, as you can see here, were hollow cylinders of 8 inches diameter with 4 3-inch flange faces that were drilled to take bolts to connecting pieces. The water would drain through these columns. And as I said, the speed of construction was incredible. 7 hectares, made watertight in 27 weeks. If anybody's ever had any building work done in their house or whatever, pretty remarkable to achieve that. 1851. So those cross braces that you see there were bolted and would have relied on a consistent thread form to allow interchangeability in nuts and bolts. But that wasn't possible at the time, or was supposed to be not possible, as you can see here. Here is the great James Nasmyth, inventor of the steam hammer. Nasmyth said, "There was no system observed to pitch, i.e. the number of threads to the inch, nor was any rule followed as to the form of the threads. Every bolt and nut was thus a speciality in itself, and neither possessed or admitted any community with its neighbours. All bolts and their corresponding nuts had to be marked as belonging to each other, and any mixing of them together led to endless trouble, hopeless confusion, and enormous expense." Now, Nasmyth is not being hyperbolic here. This is how it was. Nuts and bolts had to fit each other. William Fairbairn said the same. He said, "As machinery advanced, much inconvenience was found from the varying sizes of the threads. Screws of the same diameter differing so much in this particular that it was scarcely possible to match a male and a female screw unless they were actually made together. Parts interchangeability did not happen." Now, prior to 1800, you could see why this was a problem. The machinery was not really there to make consistent screw threads. And as I'd said, as Keith Gilbert had said, in 1775, the machine tools available to industry hadn't really achieved much beyond that in the Middle Ages. But after then, by 1850, the majority had been invented. So let's look at the kind of machine tool that you'll use. So here we go. Here's the ancient lathe. This is the drawing that you often see. Go into a forest, find 2 trees, and you can make a lathe. You can make a pole lathe. And here it is, an ancient machine. Goes back deep into antiquity. You can see it here. Again, a pole lathe. Slightly more advanced, being used by the medieval period by a worker here. Again, note there's no tool rest at all. But the foot is working the pole, is working the driver there for the turned piece. If you visit Sharp Cathedral and you've got sharp eyes, you can look up and you can see some stained glass there in Sharp, some 13th century stained glass, and you can find a turner. There's a woman turner there, again on a pole lathe. So this is the technology of that period. But we have to, let's move forward a little bit. So you can turn on it, but there's no tool rest, and there's no lead screw. What that needs is this progression. So you can see this drawn on the left, drawn by James Nasmyth that I mentioned earlier. Here you can see a turner on a lathe without any tool rest whatsoever. Moving on, you can see the turner relaxing by his machine, looking like life has been made much easier by the fact there's a tool rest there. But then look forward to the next machine, 1816, made by Richard Roberts, prominent display in Kensington, the Science Museum. A machine still capable of work when you look at it. If you look at it, that's got a lead screw. What that machine does is establish a relationship between the turned object and the cutting tool through gears. That means you can replicate that gear train. That means that somebody in Bolton or somebody in Boston or somebody in Baltimore, it doesn't matter. As long as they replicate that gear train, they can make the same thread as you. They can make the same number of threads per inch. That makes it, that means that you can replicate the threads. But this doesn't happen straight away. So here you can see some screw cutting at the top there. Here's the innovation, Maudslay. Around about 1798, 1800, you can see, again from the Science Museum, Maudslay's lathe with that lead screw that will establish that relationship between the turned object and the cutting tool. And I had the privilege of going to the Science Museum archive where I measured some of the taps that Maudslay made. These taps are from around 1800. And they're remarkable because here you see a new technology being explored for its capabilities. Some of these taps are 100 threads per inch. Remarkably fine threads are being produced there. Even Whitworth's millionth measuring machine only uses 20 threads an inch. You can see that Maudslay is experimenting with very fine threads, must be for measuring equipment, but there's a lot of experimentation going on. And the Science Museum began collecting these, as you can see, around about 1925 from the dates of the numbers. But, a real important part of our industrial heritage, that archive, because these could be produced by Maudslay after the invention of that machine. I say invention of the machine. It's one of these things where, at the same time, somebody in France was probably working on a lead screw lathe and somebody in America. Somehow, without talking to each other, this was in the air. But Maudslay gets the credit. So, as I said, Whitworth wrote this paper on standards. And he wrote about how there's great inconvenience found to arise from the variety of threads adopted by different manufacturers. So he wanted to come up with a standard that would be palatable to the factories throughout Britain. And so to do that, he realised that he must, as closely as he could, replicate what was already happening out there. So he gathered together nuts and bolts from the principal factories around Britain and measured them. And he found that the average angle in the threads was 55 degrees. And he found the average number of threads per inch for each size, say 7/8 or an inch. And what he did is he averaged that because he knew that if he tapped into existing practices, it would be most likely to be picked up. And that's indeed what happened. Now, Whitworth's method of using vernacular, native workshop practice to ensure the likelihood of his standard being adopted was an approach that Charles Babbage, the inventor of the mechanical calculator, the difference engine, which Wordsworth, as well as Byron's daughter Ada Lovelace, worked on, approved of. And you can see Babbage here. Babbage went to Cambridge University, but nonetheless, he saw where innovation was coming from. Babbage says, those who enjoy leisure can scarcely find a more interesting and instructive pursuit than the examination of the workshops of their own country, which contain within them a rich mine of knowledge too generally neglected by the wealthier classes. If you want to find innovation, go to the workshops, not the universities of the time, go to the workshop for engineering innovation. So, as I said, Whitworth aimed for a common standard. But this standard needed the kind of technology that had been created by Maudslay in 1798, establishing that geared relationship between the turned object, held in a chuck or faceplate, and the cutting tool secured in a tool post, travelling on a lead screw. So let's think of some of the other things made in the period to show how necessary it was. If you look at the rocket of 1829, Michael Bailey and John Glithero measured the rocket. It's been in an industrial artefact since 1862. It took until they measured it in 1999 before anything was really established. Nobody had taken the care to do that. And what they found was that every nut and bolt was different. Even in one machine, every nut and bolt was... The nuts and bolts were mated to each other, and none of them would fit any other nut and bolt there, even in that one machine. the rocket. And that persisted until Whitworth's time. Whitworth's paper, as I said, received widespread dissemination after it was published in the Threepenny Mechanics magazine in October 1841. From then, the standard was quickly adopted by companies wishing to cut down time and waste by utilising the interchangeability of the Whitworth thread. So, the palace. I'm going to now describe some of the work that I carried out after meeting Ken. So I wrote to Ken at the Crystal Palace and I said, do you have any nuts and bolts from there? And he got back to me and said, nobody's ever asked for the nuts and bolts of the palace, but he found some. And he posted them over to me. And here's one here. This was the first one that I measured. And you can see what a mess it was. I didn't want to do anything destructive with it. I know that could have been done, but I didn't. So it was soaked in oil and using heat and a lot of force. Eventually, they came loose. And they were measurable. The standard of the nut was actually quite good. And I measured them, and I could see that this was a 7/8 Whitworth thread. You know, there was 9 threads an inch. The angle was 55 degrees. It was a 7/8. I then asked around for other people to verify the measurement. There weren't really very many people around. I found even I went to the Science Museum archive. I measured some of the bolts from Richard Roberts' lathe. He used the kind of odd size, like half sizes, like 13.5 TPI and things like that. There's not, probably in this room there are people that would do it, but I didn't find many at the time. So how could I prove that this was the Whitworth standard? So I kind of had to make one. So this was a further test. So what I did is just turned it, bit of steel to 7/8, undercut it, hand ground a tool to the 55 degrees, and then followed the Whitworth specification of 1841, which was a 7/8, 0.875 OD, a 0.737 root diameter, and a 55 degree thread rounded at the top and bottom. So the thread fitted, it fitted the old nut, fitted the bolt, and back and forwards. That's the Boxford that I did this work on, an old 60s lathe. Here are some more threads that I measured that Ken had got for me, and you can see here the old nut fitting on the new thread. And as Fairbairn said, in the present day, to form an ordinary screw thread, he's writing in the 1860s, with any size on Whitworth standard, is little less than a crime in the eyes of educated mechanical engineers. So this is workshop practice, but it's not yet sanctioned by British standards. So the first meeting of the British Engineering Standards Committee, later the British Standards Institute, fell on the day that the Victorian age ended. That was the 22nd of January 1901, the day that Queen Victoria died. That's the day they met. And they subsequently adopted the British standard Whitworth screw thread in 1905. That's when it was sanctioned. And this has been successively updated. And the foreword of the 1956 update to the standard, BS 84 1956, ends with, Whitworth threads will undoubtedly continue to be used for many years, especially in replacements of spare parts. In 2007, it was again updated, and they wrote, the present revision of BS 84 has been undertaken because 50 years on, this continues to be the case. But in fact, the Whitworth thread's not only used in repairs. If you see scaffolding in the UK, Whitworth thread. If you see a camera tripod, Whitworth thread. Light fittings, microphone stands, it's still being used and manufactured. And still the British standard pipe thread uses a Whitworth thread. So that standard suggested in 1841, utilised at the Crystal Palace so that it could be built quickly and use 30,000 nuts and bolts, still persists to this day. Now, as I said, technical objects like nuts and bolts seem distant from the human, based in theories and standards set from above. But the Whitworth thread has human workshop practice at its centre, and its form has influenced all standard thread forms since. This is my last slide. I'm going to talk about touch, the true plane, and the millionth measuring machine. Whitworth stated that next importance to the true plane, flatness, is the power of measurement. And at the Crystal Palace, Whitworth demonstrated his millionth measuring machine, which you can see there. And this was about the shift from sight to touch and measurement, which Whitworth brought forward. And he said, I make standards of size by a system of measurement dependent for its accuracy upon a space presented to the eye, presented by touch rather than to the eye. So he said, my experience has satisfied me that no system of measurement depending on the power of sight is suitable for obtaining the size of the working parts of machines where exact size or good fitting is required. So why do they want this? Well, it's efficiency. You need more efficient machines. That means more accuracy. And it's worth giving a sense of how accurate sight can be. So when I was an apprentice, I was trained to be able to measure with a steel rule to a 64th of an inch. That was it, 64th with a steel rule. So that's about 17th down, or the thickness of 4 bits of writing paper pinched tightly together. That's what I was told I could achieve by my. But Whitworth demonstrated that through touch, you could measure to a millionth of an inch. So 4 bits of writing paper by the eye, 64th standard, apprentice, steel rule stuff. But that's this piece of writing paper divided 4,000 times. That's a millionth of an inch. 4,000 times. That's how accurate it was. And as Whitworth wrote, it's such a small amount that even rubbing a bit of soft steel with your finger will take a millionth of an inch off. That's how tiny this machine could measure. And you can see how he did it. You've got a 20 TPI thread, again, possible because of the modular machine. You've got a 200 tooth wheel, 250 micrometer divisions. That's a millionth of an inch you can measure to as you turn that wheel. So what Whitworth did is he put a standard yard into the machine when he was demonstrating this at the Crystal Palace. And what he did, and so the standard yard, I should say something about that. There were various yards constructed, and until the end of the 18th century, the standard yard could be plus or minus a 16th of an inch, or 67th thou. That's how inaccurate the standard yard was. And by 1824, the Weights and Measures Act had the standard yard at 62 Fahrenheit, and this was the imperial standard yard. It was, as Whitworth noted, the only standard available. It was destroyed in a fire in 1838 and remade in 1845 using yards from the Royal Astronomical Society and the Ordnance Survey. So Whitworth said, these yardsticks are pointless, they're only good for woven goods. But he used one nonetheless in his demonstration. So what he did is he put it between the anvils of his larger millionth measuring machine, and the standard yard just fell through. And then, a little bit of theatre, he just touched the end of the standard yard, and it seized within the anvils of the measuring machine. That was to demonstrate just how accurate it was. Even the momentary touch of his finger was enough to make it expand so that it would stick between the anvils of that measuring machine. With that tiny, tiny touch, that tiny human touch on the bar. And what he said, and what he advertised of his factory, was that in his factory, they made gauges where his workers measured to a 20,000th of an inch. So again, this was a great advert for just how wonderful his factory was, but also it pointed the way forward to that shift from sight to touch. Okay, I'm going to conclude. I'm coming to my conclusion. So in this talk, I've discussed the relationship between vernacular practice and theory. Whitworth was a genius, obviously, but that's not why I'm here. Part of his genius was to refine and disseminate the best of established practice. He looked at what was happening around him, and he disseminated the best of that. That three-plate system, he no doubt learned that at Maudsley's Lambeth factory. But he refined it, and he published on it, and he opened it up to other people and established standards for flatness that persist to this day, and give the lie to some extent that machining and grinding can produce a surface that's superior. We can see in that recent work that over a distance, scraping still produces superior flatness. And it was again from Maudsley's innovation of the screw cutting lathe and trying to establish, to some extent, standardised thread forms within his factory that led Whitworth to coming up with thread forms that would allow a global engineering industry to emerge that used standardisation long before it was sanctioned by British institutions. And finally, the need for accuracy to improve efficiency led to some of that screw thread technology being used to shift measurement from the eye to touch to achieve the highest accuracy. And that efficiency, I mean, there's another stat from the period that I really want to tell you. It's by 1870, they'd made steam engines so efficient in shipping that they calculated that burning one sheet of writing paper could move 1 ton 1 mile. That's the kind of efficiency that they reached by the late 1870s, early 1880s. So the philosopher Gilbert Simondon notes that there's a xenophobia against machines due to non-knowledge of their nature, and argued that the machine is the stranger inside which something human is locked up. And what I've done in this talk, examining truth, threads and standards, is to try and find that human locked up inside technical objects and engineering practice. Thanks for listening.
Thank you, John. That's given some food for thought, I'm sure. If people are online and want to ask questions, are they using the chat, Dan? Yes. Enter your questions in the chat. Dan will pick them up, and we may be able to page you in and you can talk to us, or we'll find some other way of dealing with questions. You're happy to take questions, of course.
I'll take some questions, yes.
So, questions in the room? Someone must.
Observations are fine as well.
Observations are fine as well. Any nuts, bolts?
Yeah.
Bottom nuts?
How flat was the flat?
So I did the figure that I could get it to within a nanometre over. So in that book that I looked up on it there, it could be to within a nanometre. But as I said, that mercury mirror, I could send you the reference to it. I don't have that exactly, but even that mercury mirror isn't exactly flat because of the curvature of the Earth. But that was held as the standard in Germany still. But yeah, I had cut. It's in my computer actually. I could find it for you if I look at my computer and look it up. But I had cut that bit from the. I had that in the quote actually, and I cut it. But it was a nanometre. But I think it was over a 50 centimetre length.
Nanometre sounds quite small.
Yeah, yeah.
Is that micron or tenth micron?
Yeah, it's remarkable. It's remarkable. But I'll send the reference. I'll be happy to send the reference because I do have it there.
I remember one of the courses I did when I was at university was metrology. And you got into trying to measure small things. And one of them was they gave you a surface plate, surface table, and suggested you measured it. And of course, the last thing as an undergraduate you thought of was that this flat table was anything other than flat.
I do, yes.
And then you set about finding all these small deviations. And then your mind goes slightly bonkers because you're not quite sure what you've just done that was measured off the surface table. But they were very small dimensions then with a modern surface table. I guess now you do it with light.
One of my colleagues, Sam McMaster, would know. He's an expert in tribology and the surfaces, and he would definitely know. But I could send you that. If you give me your email at the end, I can give you the information. What Whitworth noticed actually was because you end up with this mottled effect on the surface plate, people would fake them. So they would just do the mottled effect so it looked like it was perfectly flat, but it was a fake surface plate. So even then, there would be fakery. But he had that test, of course, where you slide them together and atmospheric pressure keeps them together, or just lower one on top of the other until there's a pocket of air. That will only happen if they've got a really high degree of truth.
But the interchangeability question is the one that comes through all the time, isn't it? You do like your spare parts to fit what you're trying to fit your spare parts to. I speak with lessons from the past here, Alfred.
Yeah, I've got a question, one question, and also an observation to make. I'll give the question first, and then I'll ask the point. The Whitworth thread has become obsolete, I understand. Why is that?
It's still used. I mean, it is still used, but it's used for, as I said, things like scaffolding. It's become. I mean, it's an imperial thread. You know, we've moved on to pretty much use of metric threads as well now, but it is still used in some practices. It was pretty much copied in America. And so the American standard thread did copy it, but what they did is they changed the angle to 60 degrees rather than 55, and instead of the peaks and troughs being rounded as with Whitworth, they became sharp. So it's an inferior thread, the American thread, still used, because it's got these stress concentration points, whereas the Whitworth doesn't because it's rounded. So it's still got huge influence, and it's still being used and manufactured, and they've updated the standard. But as I said, in that shift to metric, it's kind of it has fallen away. And oddly enough, that factory that I showed you, some of the drawings that we would work to in the 90s, some of them were older drawings, and they'd be a mixture of imperial and metric parts and measurements in it. There were hybrid systems being used, where you could get a metric machine using Whitworth nuts and bolts, and sometimes that persisted a long time.
Right, thanks. There were people going for very high accuracy before Whitworth, and these were the people making astronomical telescopes and mirrors, in which very high accuracy on very funny curvature. For a telescope mirror, it's got to be parabolic, and it's got to be accurate to, I think it's either a quarter of the wavelength of light or an eighth. And this was being achieved, well, my memory's gone now. The man who discovered Uranus, Herschel, with a 48-inch mirror. How was he doing that?
Do you know what? I don't know. I mean, that workshop, the genius of that individual workshop practice. What Whitworth did, I suppose one answer to that is, what Whitworth did is he democratised accuracy. He showed ways of doing it, that he could democratise it across Britain and make it into that engineering powerhouse that which then spread around the world. I think what you're describing is superb workshop accuracy based on highly trained, highly skilled people. But as far as optical accuracy goes, I have no notion, no knowledge at all. But that sounds to me like a very discrete and fugitive knowledge, the kind of knowledge that only certain people in guilds would have, and would be very few people could achieve that. I think one difference that Whitworth's doing is democratising a kind of knowledge.
Yeah. Thanks.
Thank you. That's a great point.
So, provocative question. Was Whitworth not entirely altruistic, and was he really actually just advertising his factory?
Did he have feet of clay, like all human beings? Whitworth, I've supervised a lot of PhDs, and if anybody ever tries to sort of go, be bad to their heroes, I say, please don't do it, just leave it. Celebrate the stuff they've achieved and they've done. I think that no doubt Whitworth's fame brought him riches, and he was a knight of the realm, and his factory became famous, and his standard became famous, and after he died, it was named after him. I think you can hold both of these truths at once. I think there's a kind of negative capability going on here where at the same time, he could be altruistic and democratise, and at the same time benefit from that altruism. I think both of these things can coexist in the one person. But he was a deeply practical man, and he always, because he came from the working classes, left school at 14, went into an apprenticeship, he was sometimes, some of the descriptions of him from people in the upper classes and upper middle classes could be really disparaging when he walked in the room. He did suffer a certain amount of prejudice as well as he moved into these realms. But yeah, did he benefit? No doubt. Did the rest of us benefit? No doubt.
We now use metric threads. Would I be right in thinking that those originated principally in Germany? And what was the prehistory of this sort of thing in Germany as distinct from in Britain?
Oh, that's a hard one. Jocelyn Holland wrote a good book about 10 years ago called The Lever as the Instrument of Reason, which is about late 18th century German engineering practices. And there's another one by Helmut Müller-Sievers with a brilliant title. It's just called The Cylinder, and it's about German engineering. I mean, I think when it comes to the metric system, of course, it comes from France. It comes from, you know, that relationship which is not correct on, you know, diameter of the earth and all the rest of it, and the distances, and yeah, it developed from there. But I think, but no, that standard, the standard started in Britain. I mean, yeah, metric systems come in later on, but I don't know anything really enough about Germany. I've only read those two books, and they would precede all of that because they're pretty much about the 1780s, 1790s in Germany. But no, that would be interesting.
You're sort of conflating two things there, aren't you? You're conflating standardisation,
yeah,
and the dimensions that went into the standard, if you like.
Yeah.
So the Whitworth thread form, from my recollection, is if you get the right sizes, a metric thread and a British standard Whitworth thread, as long as the pitch is about the same, you can actually make a pretty good job of ramming them together.
Well, ramming is the word, yeah.
Yeah, but if the pitch is the same,
I know,
the thread form's not so different.
I do know the size. If you've got a 5/8 and a 16mm, yeah, you can kind of make it fit. But the angles are different. 60 degrees on a metric and 55 on a Whitworth. It's really very poor practice.
Yeah.
It's like using a shifter for everything. Just use the right size spanner.
I just wondered whether, in fact, when Whitworth and the standardisation, it must have influenced other parts of the engineering world. I was partly thinking I once had a set of lithographs prepared by Daniel Gooch for the Great Western Railway in order to make sure that all the parts were standardised. So is there a sort of, we talk about Whitworth and standardisation, did it spread willy-nilly into other parts of the engineering world?
I think it was in there. It was certainly there, and again, war pushed it. The Crimean War pushed it. There was a ship that was discovered, and they pulled up the engine. The engine had been used in the Crimean War, so 1860, 1850s, and the engine used Whitworth threads. And yet, an engine from 10 years before wouldn't have done. So yeah, war production definitely drove that as well.
War and Human Progress, which is a fantastic book, and you might well look me up to see about standardization.
Yeah.
About the invention of sterile weaponry, but it's a wonderful book.
Yeah. Having parts that could be replicated became very important then. But yeah, it was certainly in there, that notion. And as I said, the girders, the beams at the Crystal Palace were standardised, so that it could be achieved. So it wasn't just the threads, it was throughout the building.
But it's all about the move from bespoke to production, isn't it?
Yes.
We have a question out there in Cyberland from John Glitheroe.
Oh,
If I can work the sound mixer properly, John, if you'd like to unmute yourself and ask your
wow.
question, we'll see if it
Amazing.
works.
This is testing
Hello, can you hear
electronics,
me?
not anything to do with screw threads.
Hello? Hello?
I'm afraid we seem to be having
can
some
you hear
trouble
me?
with that.
Just a moment.
Could you type your question
people-
into chat, John, and I'll read it out down here?
Right. Or can you hear me
Ways are the
now?
good ways.
I can do it. Oh. Unmute. Are you able to hear
I'm
me
not sure
now?
whether you mentioned this when you were talking about the Crystal Palace. How many bolts were actually needed, and how many companies and lathes were actually being used to produce them? I mean, looking at the pictures, I would have thought there's not that many. There's a lot, but not millions, maybe thousands.
about 30,000, Ken, calculated.
40,000.
About 30,000. Ron Granger was very good in looking into that and trying to establish something plus or minus 5,000. So there'd be about 30,000 nuts and bolts. There was an engine on site that would work. There were lathes, obviously, for facing and screwing machines that were there as well, that were used. But yeah.
So did they have all the lathes and so forth actually on site?
There were machines on site,
Really?
yeah. Yeah, there were machines actually there, but they'd been made in factories elsewhere as well. But I know that they had some machines in site. But no, you're right, they wouldn't all have been done there. They'd have been, because you could follow the standards, you could do it in any number of factories. But I've been on, that's fugitive information for me. I don't know the different factories that did it other than, Fox Henderson and, you had the machines in site. But there is, I had the information on the size of the engine, the main engine in site, how many horsepower it was that was being used to power other machines. But beyond that, I don't know a great deal about where they would have been produced.
I mean, I was just thinking it isn't that quick to actually make a threaded bolt.
Well, they had screwing machines that they made that would just be set up for it. You make a setup and, yeah, you go from there. And you can also make up dies with some of the small ones as well, but yeah.
Yeah.
But yeah, no, they achieved it, yeah. As I said, it was Ken Cass that worked out the number. So thank you.
Yeah, we've actually found the question and answer session. Sorry about that, folks out there in Cyberland. Chris Tootle has made the observation that at least one specification of Whitworth's threads precedes his paper. Mm-hmm. Daniel Gooch knew him and specified the threads in the specification for the Fireflies. He also had an accompanying drawing with dimensions of hexagonal and square heads, and that would have been around 1839.
Yeah.
Yeah.
Yeah, I mean, there were factories that were setting up their own standards, and that's how this was achieved. As I said, he pulled in nuts and bolts from the principal factories that were around, and he took the average. So some would have been hitting that standard. As I said, the Roberts lathe ones that I measured from about 1817 were not a million miles away. The angle was different. The angle was about 60 degrees, not 55. But it was only a couple of TPI out, the ones that I measured from the ones that Whitworth later came up with. So you can see a kind of, through practice, that a standard beginning to be established. And that's how we managed to catch the imagination of all the principal manufacturers, because he tried to replicate what they were doing already. He averaged what was out there. So yeah, that's a good point.
Yeah. John Glitheroe mentioned that when they examined the bolts on rockets, they found that some of them were cut with a die and not a single point tool.
Yeah.
And obviously all the ones cut with the die would therefore be the same.
Yeah.
But for some sizes there were two different pitches. We assumed that these were later replacements. And he found similar when he measured some Roberts threads with Richard Hill's.
Oh, that's such useful information. Yeah, it's such a wonderful book. John Glidrow and Michael Bailey produced, and I remember that passage where, you know, they talked about how some are cut with a single point tool, some have been cut with dies, and it's trying to work out what period they came from. But yeah, that's as you said, if you're going to cut it with a die, it should be the same size for each.
Yeah. Chris Tuto.
That's really useful.
Added another anecdote from his father's time in apprenticeship, early in the career in the 50s, was that the factory pipe fitter would turn all his 11 TPI threads by hand using a chaser as it was quicker.
Oh, yeah.
David Brown has commented, excellent paper. Brings to mind the time I started workshop practice at Tech College in '62, scraping flat surfaces and learning to make good screw threads on a lathe.
Yeah. There you go. Thank you.
That there, Dan?
There's one other from Eric White. Great paper, John. Was wondering if you could say a bit more about the wider cultural response to Whitworth's engineering, innovation rather. How much did artists and writers know about vernacular standards? This is wandering off into philosophy a bit. And did they recognize any of his and his workers' practices in their own?
Ooh, thanks, Eric. I mean, Whitworth became famous because of this, as I said, and you know, the adoption of a standard, did it move into the arts and literature? Oddly enough, I've been looking at recently. I was in the Whitechapel Gallery about a month ago, looking at the archives there, because in 1945, during the election month that Labour won, an exhibition went on that was by the Amalgamated Engineers Union. It was the first ever art exhibition by a trade union. And I've looked at the catalogue, and it's fascinating because it's machinery. It's machinery that were exhibiting during that month, and Ernest Bevan opened it up, trying to, do some work in that. And yeah, I can see how these machines from 18th century depictions of machines through to ones that are, let's say, Muirhead Bones, giant slaughters from the First World War, through to some of the latest work in the second, about how artists concentrated in machines that were producing the kind of things that Whitworth wrote about, and that these engineers would have understood what they looked at rather than the general public. They would have understood the machines that they looked at. But beyond that, Eric, I don't know how much Whitworth affected the other arts, other than things were then produced that people could buy and use much more cheaply, and it could help it in that way. But no, I need to think about that more. But thank you. Thanks a lot.
Okay. Any more?
It may be a problem with my hearing,
Yes.
but were you telling us that in Hyde Park, when they were building the Crystal Palace on the site, there were numerous artisans making threads bespoke on that site? Maybe I misunderstood that entirely.
Yeah, I don't know that exactly. I know there was an engine working there, a steam engine, and they were making some parts and some things in the site, but were they making 30,000 nuts and bolts? I seriously doubt that. They would have been made in factories around London. Yeah. Nonetheless, things would be getting made in the site when they were needed as well. So, but there's not an awful lot of detail on what was being manufactured in the site. There's some detail in the machinery in the site, but not a lot beyond that. And I wish Ken was here to fill that in. This is a bit of that fugitive knowledge that I might never really get to the heart of. But thanks.
And with the contractor faced with producing so many bolts and nuts, wouldn't a die be the most efficient way of producing those? And you seem to be talking about turning each individual thread, and would that be the method to do it? I don't think it could have been. I'm a modern engineer, so
You're absolutely right. With some of the sizes, you can use dies and you would need to use taps, but of course they would need to be to exactly the same pitch, the same angle and the same depth. So you need the kind of machinery that exists to make these taps and dies. So there's a mixture of practices going on. You can cut with screw cutting machines, single point screw cutting, or you can make with taps and dies as well. So it depends on what they've manufactured to make them. But yeah, you can do both, but it depends on the sizing as well. Certainly, even by the 80s and 90s, when I would be making these things, frequently single point screw cutting was used. You could do it very quickly if you had the setup as well. So there's a mixture of things. Taps and dies wear out quite quickly too. It depends what you've got available to you at the time as well. But yeah, you can use both.
Problem with taps and dies, of course, is they wear as well.
Yeah.
They wear. The taps and dies wear.
Yeah, they do. But yeah, you can. It depends on the sizing, obviously.
If they wear, because you're making the two together.
But then you don't have interchangeability. Then you've lost all of that. You've lost everything you set out to get.
Just moving on from that, actually, do we have any idea what the quality control was to achieve the interchangeability, given the fact there were presumably numerous factories making these?
Yeah, I would imagine it. Well, of the period you would use go and no go, wouldn't you? Probably, just as you would use into the 20th century and beyond. So Whitworth had go and no go gauges. That's what you would. So I imagine that in a batch, you would examine every so often where you're going no-go to make sure that the standard is there. That's probably the easiest way of doing it. You're going no-go gauge, which is still being used.
Of course. What surprised me most, I think, when I was a young man in the works, was that such things as bolts and things like that were sent to a special little room we had for inspection of these things, the staff of which were all blind. And it was done by, it struck me as very odd that your inspection department came in with their guide dogs and sat down and measured these things, but it was because of the power of touch. And they were extremely good at dealing with these checks on the accurate bolt cutting, thread cutting, fit limits, fits, all these things. It was a remarkable thing that made you realise just how sensitive your power of touch is. Remarkable. And that was an aircraft factory. I think we've exhausted the large number of people online. Have we exhausted everybody here? It seems to be that way. We've probably exhausted you, John, but thank you very much.
It's been a pleasure to be here. Thank you.
It's been
Such
an
a privilege.
interesting discussion, and thank you very much for contributing to that. Notices, our next meeting in London will be on Wednesday the 15th of April. It says March here. Right, that was close. A plain, substantial piece of workmanship. The marine What? Wednesday the 15th, it says. Is Wednesday the 15th in April?
It's a week later than normal.
Because of Easter, we move a week later, like most things in life. A plain, substantial piece of workmanship, the marine compound engine and the tramp ship in 19th century Britain by Oliver Carpenter.
That would be good.
Which I might be interested in. So, pardon?
You might be interested in.
I probably will be, yes. I should be. Julia's booked some dinner afterwards with you, John. And so there'll be some people going and wandering somewhere down the other side of Farringdon. Thank you all for coming.
Thank you.
Thank you for those online. And can we just thank John in the usual conventional way?
Thank you very much. Thank you.
See you next month.